Hey Earth Science, while we're studying space, there's a short and sweet little topic that I'd like to cover with you, and that is how to measure distances in space. One of the things that it's hard to escape noticing and being amazed by when you're studying space is just how vast the universe is. I mean, forget the universe, even just our solar system is beyond enormous. But then when you consider the galaxy and the distances between galaxies, the distances are mind-blowingly large. And sometimes it's worth asking, how do we know how far away these things are? Well, there are three different methods of measuring distances in space that I'd like to try to explain and then demonstrate for you as well as I can. Those are parallax, standard candles, and redshift. So parallax is the apparent change in position of distant objects as you, the viewer, change location. This is actually something that you can demonstrate right where you are, in whatever room you're sitting, whether you're outside, anywhere you are. This is something that you're able to do, and all you need to be able to do is to close one eye. So just cover one eye and take a look at some object a relatively short distance away from you. Note where it is in your field of view. You could be looking at this video right now and just seeing the position that my head is in your field of view. Now, that's with one eye. What you want to do now is, without moving your head, change which eye is blocked. If you keep your head still, but change the position of your view, just by switching eyes you can do that, you should notice that everything now occupies a slightly different location in your field of view. In case you didn't notice it, you can go back and forth rather quickly, and if you prefer, you can just close one eye at a time. You should notice a slight change in position of everything in your field of view. This is called parallax. Now, you can actually use this with some math to determine the location of faraway objects. Now, obviously, this is just something that you can do with your eyes, but how does this work with the Earth? Well, the Earth orbits the Sun at an average distance of 93 million miles, which means if the Sun is in the center and the Earth is in, say, our summer position, 6 months later, we are 2 astronomical units away, that is 93 million miles, 93 million miles, away from where we were in the galaxy, so to speak, than we were 6 months ago. So if your eyes are mere inches apart and closing one of them at a time is going to change the apparent position of distant objects, moving yourself 186 million miles apart is going to cause a similar shift in the apparent location of distant objects. Now the math is a bit more extreme because despite moving several, well, I wouldn't say several hundred, almost 200 million miles, the distance to nearby stars are trillions of miles. So their apparent shift in position will be very, very slight. However, it is measurable. And using that, we are able to calculate the distance to somewhat nearby astronomical objects. The next method of measuring distances is with a standard candle. So just as playing a source of noise right next to your ear is unbearably loud and moving it away from your ear makes it more bearable, So too, shining a light directly into your eye is very painfully bright, but from across the room is a little bit less unpleasant. Well, that's because as the energy radiates out into space, the further away you are, the intensity of those waves decrease according to an inverse square law. So that if you are double the distance, it will be reaching you with a quarter of the intensity. Triple the distance, a ninth of the intensity. What this means is you are able to tell how far away from something you are if you know its true intensity and you can compare that to its apparent intensity. In other words, if you know how loud a sound ought to be if you're standing right next to it and you hear it quiet, well, then you can calculate how far away it must be in order for it to have that volume. Similarly, if you know how bright an object should be and yet you see it dimly, you can calculate how far away it must be in order to appear that dim to you. The question is, how do you know how bright certain things ought to be? Well, there are two types of standard candles that astronomers have used, and one of them is a supernova. You see, a supernova is the collapse of a star as it's exhausting its primary fuel, and it can't maintain the outward pressure that comes from burning its fuel, which is running out. As the mass of the star overcomes its explosive force and it collapses, that sudden increase of pressure reignites fusion and it explodes back out in a brilliant, enormous explosion, which can sometimes be brighter than the entire rest of the galaxy that it's in. Because this is an event which is describable with nuclear physics models, we are able to predict how bright they should be. And if you know how bright it ought to be, and you view it at a different brightness, a good explanation is that it is a certain distance away. The last way that we have of measuring distances is most useful for extreme distances. You see, for parallax, that only works for our neighbors in the galaxy, because once you get a certain distance away, the slight separation between your two vantage points isn't enough to make a measurable difference in its apparent location. And standard candles are only useful within a certain range because past a certain distance, they won't be bright enough to detect, or the difference between two different distances may not register. However, one fact about the universe that we've known for a long time is that it is expanding. And because it is expanding, as a distant galaxy moves away from us, as the space between it is stretched, the light between it is also stretched. Now, a nearby galaxy's light has been stretched a certain amount as it's traveled from there to here. However, a more distant galaxy's light has been traveling through much more space for much longer, which means it has been subjected to more stretching. Now, what effect does this have on the light? If you remember from our discussion of false color images and the electromagnetic spectrum, you know that different wavelengths of light are able to help us to distinguish them. In other words, you can have light with a high frequency and a short wavelength, and then light with a low frequency and a long wavelength. Well, what happens is, as the light is traveling through space that is stretching, the wave becomes stretched, and that means that its wavelength increases. Because red light is the visible light with the longest wavelength, we say that it has shifted in the red direction, and so we say it is red shifted. Now, even if that light is not visible, we still say it's red shifted simply because it's changed in that direction. So, what light has been red shifted, and how do we know that it has been shifted? Well, because we know that stars are made primarily of hydrogen, there are certain wavelengths of light which are emitted by hydrogen, and they form a kind of fingerprint for hydrogen. This is how helium was discovered on the sun, by its unique atomic fingerprint. Well, by this unique fingerprint of hydrogen, you are able to identify a altered fingerprint. In other words, looking out to distant galaxies, expecting to see hydrogen in one part of the electromagnetic spectrum, to see it shifted down a little bit, it's clearly red shifted, and you can calculate how far away that galaxy is based on the rate of expansion and the degree to which it was red shifted. Those three are different ways of measuring distances within the observable universe. They operate at different scales, and to the degree that they overlap, they agree. There is a phenomenon in science called concordance. Concordance is when multiple independent lines of evidence converge on the same conclusion. Concordance is a great strength in scientific research, and it's one of the reasons why we can be so confident that when we have a measured distance, that we have it correct, because we've measured it twice with two unrelated methods that the same error cannot corrupt. And if we have some that are confirmed with both measurement types, then it gives us confidence in those measurement types, so that if something is measured with only one or the other, we have some confidence in them from where they agree. Anyway, this is just an explanation of how great distances in our universe are measured. Hopefully you found it informative or interesting. Anyway, that's all for today.